We are on chapter 12, and chapter 12 is all about groundwater. This is a beautiful picture of Mammoth Cave, and you can see all these stalactites and stalagmites shown within the cave. So what do we actually mean by groundwater? Well, groundwater is that water that's underground. It is stored in the pore spaces of soil, sediment, and rock. It only constitutes about 0.63% of the world's water, so not a great amount. The ultimate source of groundwater is in the oceans. Other sources would be any water precipitation that infiltrates the ground. Streams, lakes, ponds, swamps are all sources of groundwater. One term we have to make sure we understand, and that is porosity. Porosity is the percentage of a material's total volume that is pore spaces. So you're looking at the spaces between the particles. You're looking at cracks, fractures, vesicles. Water is going to soak through those pores. Now, depending on the soil type, the rock type, the fracturing, the weathering history will depend on your porosity. Picture C is showing us in a soluble rock, like a limestone, porosity can be increased by solution. Notice our pore spaces in all these open spaces. In picture D, you're looking at pore spaces that created by fracturing. So you can see all the light blue is where your water, your groundwater is being funneled. So this chart shows you porosity values for different material. Notice that it's going to depend on whether your material is unconsolidated or whether you're dealing with rock. Soil, for instance, has about 55% porosity. Clay has only about 50 to 70% porosity. Whereas if you look at a shale, the porosity is very low because a shale doesn't really have many pores in that type of rock. Now, our detrital sedimentary rocks, those that are composed of well-sorted, well-rounded grains, they are going to have a higher porosity because of where the two grains can touch. They can only touch at a single point. You can see in picture A, notice these well-rounded grains, they're only touching here. Those are only touching here. So all that blue is pore spaces. So well-sorted, well-rounded would have a higher porosity. Whereas if we look at picture B, poorly sorted sedimentary rocks are going to have a lower porosity because notice poorly sorted means we have a wide range of grain size. Notice all of our smaller grains that can fill in the holes between these larger rounded grains. So we're reducing the number of pores. So this has a high porosity. This picture would have a low porosity. Now, permeability is another important term, and that's the ability to transmit fluids. Permeability depends upon porosity, the size of the pores or fractures, and the interconnection. We can have a rock, piece of sediment, that has a lot of pore spaces. If those pore spaces are not interconnected, the permeability is going to be very low because the water can't transmit from top to bottom. You can see in this picture the permeability is pretty good because here's my stream of water, and notice, look at where all my water is coming out. So the pore spaces in this case are interconnected, so it would have a high permeability. Now, when you look at some terms related to permeability, we have what's known as an aquifer. An aquifer is a permeable layer that transports groundwater. Aquifers are well-sorted, well-rounded sand and gravel. These would be your best aquifers. Also some limestone with fractures and bedding planes that have been enlarged by solution are also good aquifers. Notice in this picture, this is your aquifer. So your aquifer is that transport. You can think of it like a canal where the water's flowing. The aquiclude, shown in this picture, is going to prevent groundwater movement. So your aquiclude is typically your shales, a lot of your igneous and metamorphic rock, and that is because they would have a low permeability, so the water can't be transported. So here you can see there's not a connection of water from top to bottom because of this aquiclude is going to prevent that water from moving. Now, the water table is basically a line, a surface that separates two zones. It separates what is known as the zone of aeration from the zone of saturation. So right here is my water table. Okay. Now, the zone of aeration is this top zone. If you notice in this little circular diagram, the zone of aeration shows that the pore spaces are partly filled with water and partly filled with air. So it's going to have your suspended water. That water is going to adhere to the material. Whereas when I go below the water table, I get into the zone of saturation. If I look again at this picture, this little circle, I see that all the openings, all the pore spaces are blue, which means all the pore spaces are filled with water. Right above the water table, notice you have a little zone that's called capillary fringe. That is right above that zone, and that is where your water moves upward through the action of capillary action. So basically that is where instead of water moving down, right in that little zone of capillary fringe is where water is going to move up. Okay, now notice in this picture your water table is a straight line. The water table is not a straight line. Okay, the water table configuration is going to replicate the overlying land surface. So it's going to be higher on hills, lowest beneath the valleys. So I can't just take a straight line and draw where the water table is. The water table is often flat in arid or semi-arid regions. And now keep in mind, the water table is going to fluctuate. And that fluctuation is going to depend upon the precipitation, the permeability, as well as the groundwater movement. Groundwater is always going to be moved by gravity. Gravity is going to take and pull water downward. So water is going to move downslope along the slope of the water table. Water moves from high pressures to low pressures. So your velocity can be anywhere from about 250 meters per day to less than a few centimeters. Here again, it depends upon permeability. So we can see how this is a high pressure area, this is a low pressure, so our water is moving from that high pressure to our low pressure. Okay. Now, when I take out groundwater, it's going to come from discharges, flow into streams, lakes, swamps, springs, wells. When I replenish or when I take and I add water to the zone of saturation, that recharge is coming from rain and melting snow. It's also coming from recharging ponds or wastewater treatment facilities. A spring is when your water reaches an impermeable layer and it then starts to flow laterally. If the flow intersects the surface, the water will discharge as a spring. So here my water is coming down, okay? It is going to reach this impermeable shale bed, and that is going to make my water flow laterally. Whenever that water intersects the surface, I can have a spring. Okay, spring can also occur when we have what's known as a perched water table. So a perched water table is when you have a local aquiclude present in a large aquifer, kind of a lens of shale within the sandstone. So springs are natural. Man doesn't have to do anything to get water from a spring. Wells, on the other hand, we actually have to dig or drill down into the zone of saturation. So you can see here the reason why this well and this well are dry, because they do not go in that zone of saturation. What happens with these two wells that I've circled, you have what's known as this cone of depression. So what happened here is the rate of water withdrawal from a well exceeds the rate of water inflow. So your water table actually gets lowered. We see that when we overuse wells, when we deplete groundwater, we're going to have the lowering of the water table. So the only well in this picture that would pump water would be this one right here that I've put a check mark. An artesian system is a system where groundwater is confined. It builds up high hydrostatic pressure. Hydrostatic pressure is fluid pressure. It occurs when your aquifer is confined between two aquicludes. So your aquifer is exposed at the surface. The rocks that tilt are going to build up the hydrostatic pressure. And basically, elevation in your recharge area is going to define that highest level that water can rise. Artesian pressure surface always slopes away from the recharge area. So you can see here are your shale aquicludes. Here is your aquifer, so water is actually building up in that pressure, building up between those two aquicludes. Okay, and notice here's your aquifer flowing right here. We do have erosion happening, and erosion is common in limestones. Limestones are a common sedimentary rock. Limestones are composed of calcium carbonate, so they can be easily dissolved by carbonic acid. So if I mix water and CO2, I get carbonic acid. Now that erosion is going to create karst topography. By the way, CO2 is in our atmosphere, in the soil, in the air. So that mixes with water and you get that natural carbonic acid that can cause erosion. A karst topography is developed by groundwater erosion in areas that are underlain by soluble rocks, such as your limestone and your dolostone. So karst topography are characterized by caves, by springs, sinkholes, solution valleys, disappearing streams. Typically, it's going to be related to humid and temperate climate. So here showing your caves. Here is you see your solution valley here and here. Circles indicate your springs. Underlines show your sinkholes. And then finally you have your disappearing streams. This next picture is a good picture of your karst topography in China. And this is a very high relief karst topography. Okay, that ends part 1 of chapter 12.